I'll just orient you to this and go over the overview of the nephron. This is really a reference for you, and so I'll orient you to this reference. So first of all, you'll need to, know the basics of nephron anatomy. So we have given you a schematic representation of this with the classic hairpin turn that juxtaposes this macula densa, this specialized section of the distal convoluted tubule that connects glomerular function with tubular function. Eleanor Lederer went over this tubular glomerular feedback that arises from this special anatomy. The two, macula densa and this afferent arteriole, are called in total the juxtaglomerular apparatus. You have proximal tubule, which is divided into early and late, and have different transport properties, which we won't sort of granularly distinguish. We have the loop of Henle, of course, which has thin limbs and thick limbs. Distal convoluted tubule eventually goes into this so-called connecting tubule, and multiple nephrons start to drain into the collecting duct. Okay, and the collecting duct is divided into cortical and medullary collecting ducts, which have some different transport processes. We will discriminate those two a bit. All right, so the overview of some of the transport processes that I certainly think as students of nephrology we need to understand is summarized here. Again, early and late proximal tubules do have some differential function that we have to acknowledge. So in the early proximal tubule, we have sodium absorption that is exceeding chloride absorption. So when you have sodium absorption exceeding chloride absorption, that would achieve a lumen negative potential difference, okay? And that may further drive sodium absorption in the paracellular, excuse me, I said negative luminal potential difference. In the late proximal tubule, the reverse is true. Chloride absorption is exceeding sodium absorption. That causes a lumen positive potential difference, and that drives some of the paracellular transport of calcium and magnesium gated by claudins. Okay, so again, we recognize especially calcium and magnesium transport that's happening in the proximal nephron. We invoke that as one of the main mechanisms of calcium conservation when you're using thiazide diuretics to treat kidney stone formers with hypercalciuria. Again, this physiology is clinically relevant and is worth noting. Okay, we have phosphate absorption that's happening in the proximal nephron. It may happen in other segments of the nephron, but this is clearly where we best understand it. We have proton secretion in an antiporter sodium proton exchanger. That results in a net bicarbonate reclamation when that is coordinated with carbonic anhydrase. We have some absorption of organic ions, including citrate. Citrate reclamation is relevant to, again, patient care. We also have the absorption of formate anions and others. Ammoniogenesis happens in the proximal tubule, and that couples acid homeostasis. It's not simply a distal nephron function. The coordinated function of proximal and distal nephron is required in order to achieve intact acid-base regulation. We've gone over the interaction of K homeostasis with ammoniogenesis in multiple conversations. Some of you recognize those conversations as fairly recent. We generally see isoosmotic water absorption. So think of the proximal tubule as a bulk transport segment where you're sopping up salt and water isotonically. Okay, so a lot of salt and water reabsorption that's happening in the proximal convoluted tubule. I'm reclaiming amino acids. This is how you can develop cystinuria by dysfunction in amino acid transport in the proximal tubule. So those are diseases that we'll encounter in later conversations. Again, here's the overview that sets the stage for those later conversations. We have solute secretion that's happening, including creatinine, uric acid is both reabsorbed and secreted. We have drug secretion that is occurring in the proximal nephron as well. Again, more isoosmotic water absorption in both the proximal and late proximal, in the early and late proximal convoluted tubule. What about the later segments? We have a thin descending limb of the loop of Henle, right? In this segment, I'm reabsorbing water via aquaporins. We think about regulated aquaporin mediated water transport in the distal nephron. You have aquaporins throughout the nephron, including the proximal tubule. We have them in the limb, the descending limb of Henle's loop, and that is reabsorbing a lot of water as well, not just the proximal tubule. We're having sodium and potassium recycling that is happening into the lumen from the interstitium. So again, we're getting salt that is diffusing into the descending limb of the loop of Henle. Okay, now we're getting into the more recognizable parts of the loop of Henle, which you probably think more commonly about, and those are the ascending limbs of the loop of Henle. So let me orient you. These this K recycling and sodium recycling and this water reabsorption that is happening in the descending limb is part of what we understand, let's say partially understand, with the countercurrent multiplication mechanism of the loop of Henle. So we invoke that as a means for effective solute and water transport in the loop of Henle. And there's some controversy around, what actually happens with countercurrent multiplication. We at least model that phenomenon based on these principles of water permeability in the descending limb, and then this relative impermeability to water, but high permeability to salt in the ascending limbs. Okay, so think about, again, I have impermeability to water in the ascending limbs, permeability to water in the descending limb. That sets up this so-called countercurrent exchange mechanism that we invoke to model transport in the loop of Henle, model how we create a medullary hypertonicity for water reabsorption in the collecting duct. Again, this is based on these presumptions about transport processes in the ascending and descending limbs of Henle. Okay, so again, the thick ascending limb, let's focus a little bit on that because, again, that's druggable, and you should understand that more deeply because you manipulate that. The thick ascending limb is considered a diluting segment because it is relatively impermeable to water, but reabsorbs sodium and chloride and potassium through the NKCC2 transporter. That is the transporter that you block with loop diuretics. Okay, so it's a diluting segment, right? If, as you go up the ascending limb of the loop of Henle, you're reabsorbing salt, but you're not reabsorbing water, it stands to reason that the concentration of solute as you go up the ascending limb becomes less concentrated, right? I'm reabsorbing salt without water, so then I become less concentrated. That is why it's considered a diluting segment. And that would become relevant as you think about what happens to the serum sodium if I impair dilution, right? You can arrive at certain conclusions about the effect of loop diuretics on the serum sodium if you understand, well, if I'm impairing dilution, impairing the creation of a dilute urine, that would presumably make it less likely for me to dump water. If I'm dumping water less effectively, then I can become more hyponatremic. Okay, the effects of loop diuretics on water homeostasis are complicated. You can invoke rational arguments for enhanced water elimination or reduced water elimination. So again, knowing this nuance is important to understanding how both outcomes could happen, and then you can know a little bit more to understand which one is going to happen for this particular patient. You need to understand this concept of a diluting segment as one of those elements to understanding what happens to the individual patient. You have a net positive potential difference in the lumen, and that drives paracellular calcium and magnesium transport. And therefore, if you impair the creation of a lumen positive potential difference, such as with using loop diuretics, you would then enhance the elimination of calcium and magnesium. That explains how loop diuretics can help you treat a hypercalciuric patient in the oncology ward, right? Sometimes we give loop diuretics to enhance calcium excretion. We're essentially reducing this lumen positive potential difference by giving loop diuretics, and therefore reducing paracellular transport of calcium, reducing the reclamation of calcium through the paracellular pathway. This again explains why loop diuretic causes magnesium wasting and why sometimes you need to give magnesium supplements to your loop diuretics. Again, you need to know in greater detail, know it, let's say, in your sleep. Let's put it that way. You should know the others too, but you need to be able to have on the tip of your brain for teaching the resident and the student and making management decisions at the bedside what happens in the thick ascending limb. Okay? It's fair to be able to sort of struggle a little bit with the other segments, but you should know on the tip of your brain what happens in the thick ascending limb. Okay? The juxtaglomerular apparatus, we already talked about this macula densa, and the afferent arteriole and tubular glomerular feedback. You had a lecture on that yesterday. We don't have to belabor that. The distal convoluted tubule is also a diluting segment because in this segment, we still are reabsorbing salt without water. So the DCT is impermeable to water. I reabsorb salt through NCC. Again, that is druggable. You give a thiazide, you block NCC. You need to know the distal convoluted tubule as well on the tip of your brain. Okay, we do have other important transport processes that are happening in this segment. We have calcium reabsorption that's happening. We have mag reabsorption that's happening. These are some of the clinically relevant transport processes. We can get more detailed, and we will get more detailed about things like WINKs and the effect of calcineurin inhibitors on causing potassium retention. That physiology is grounded in the DCT. We'll get to that detailed version. Here are some of just the bird's eye view things that, again, you should start to commit to memory. Connecting tubule really is a hybrid segment that has transporters that are mimicking those that are found in the DCT, as well as the cortical collecting duct. You will see, for instance, NCC in the connecting tubule. You will have mineralocorticoid receptors in the connecting tubule. So those are things that you will see in this, let's call it, hybrid segment. Now we're into the collecting duct, where we're starting to see water reclamation. We're seeing ENaC. You got to know collecting duct physiology. Remember in essential nephrology, which we called essential nephrology, your first couple of lectures, I told you, all of these things that are happening at the bedside, the K wasting, the contraction alkalosis, all of those things are grounded in collecting duct physiology, the effect of spironolactone, the effect of ACE inhibitors in causing hyperkalemia. All of that is collecting duct physiology. So you got to know that also on the tip of your brain. Okay. So principal cells are one of the main cell types in the cortical collecting duct. This is the cell that transports water. It transports sodium via ENaC. It transports potassium via ROM-K and others. Maxi K or Big K is another one. So those are things to, again, commit to memory. This is where your mineralocorticoid receptor is expressed, although you do have mineralocorticoid receptor also in the intercalated cells. So we have mostly alpha intercalated cells. If you're eating primarily a Western diet that is acid rich, most of your cortical collecting duct intercalated cells are the so-called acid secreting cells or alpha intercalated cells. We do have beta intercalated cells that are base secreting cells. And it turns out that at least if you're a rabbit and you're put on, mostly an alkaline diet, most of the intercalated cells are actually base secreting cells. So these cells have the ability to, let's call it, morph into in order to achieve the acid-base balance that's required by the organism. Okay, the medullary collecting duct has transporters that are facilitating the creation of a hypertonic medullary interstitium. And then also I can secrete more acid in the medullary collecting duct as well. Okay, so that's where I would say the acid secreting cells are most concentrated. Okay, so again, we're not going to go over each segment. I'll just highlight that we have apical transporters, basolateral transporters, and not every transporter that is present is represented here, but certainly I endeavored to create, a reasonable understanding of things that are relevant to human disease. I'll put it that way. And it marches through each segment, and then the transport defect that is causal for a particular human disease. Okay, so you'll see this organized in that fashion. It goes through every segment and does the same across each segment. Okay, so this is for reference. Committing it to memory is going to be challenging. I just encourage you to keep reviewing it, especially as you're thinking about a disease. When you view in your mind a dense disease, go back to the tubular transport map and find the transporters in the proximal tubule that are causal for dense disease. Okay.